Hello students, so in this lecture also I am going to continue with the 8257, that is direct memory access controller block diagram. And I discussed about the DMA address register. I told you that DMA address, that each channel contains two 16-bit register, that is DMA address register and terminal count register, and we know there are 4 channels present in the 8257 DMA controller. Now this I told you that this DMA address register stores the memory location, stores the address of the memory location, or you can say stores the address of the memory location which is going to be accessed first, either for writing data into the memory or for reading data from that memory. And the terminal count register, it stores the count, that is number of data transfer cycles that is going to be performed. And T0 T1 will give you the status of the DMA cycle, what type of DMA cycle is being performed. Now the next block diagram that I am going to discuss is control logic. So it controls the sequence of operations during all DMA cycles, whether it is DMA read cycle, whether it is DMA write cycle or DMA verify cycle. It controls the sequence of operations during all the DMA cycles by generating the appropriate control signals and the 16-bit address that specifies the memory location to be accessed. So it consists of mode set register and status register. It consists of 2 registers, that is mode set register and status register. Now let's see the format of mode set register. So this is the format of mode set register. So the least significant 4 bits of mode set register when set enable each of the 4 DMA channels. This I am talking about this least 4 significant bits. So the least 4 significant bits of mode set register, when they are 1, they enable each of the 4 DMA channels, and the most significant 4 bits allow 4 different options for the 8257. So it is normally programmed by the microprocessor after initializing the DMA address registers and terminal count register, and it is cleared by the reset input, thus disabling all options, inhibiting all channels and preventing bus conflicts on power up. So as I have told you that the most significant 4 bits, they allow 4 different options. So what are these options? I will be discussing about them in detail in my later slides. So now the next register that the control logic contains is the status register. So as it indicates which channels, as you can see that it indicates which channels have reached a terminal count condition and includes the update flag. So this TC status bit, if 1, you can see this is TC status for channel 0, for channel 1, for channel 2 and for channel 3. Now if this TC status, and this TC status is coming from this bits of status register, B0 for TC status for channel 0, B1 for TC status for channel 1, in the same way B2 and B3 for channel 2 and 3, they are showing the TC status. Now if the terminal count, that is TC status bit, if 1, indicates terminal count has been reached for that channel, and if TC bit, that is terminal count bit, remains set until the this terminal count bit remains set until the status register is read or the 8257 is reset. The update flag, however, this is the update flag. The update flag, however, is not affected by status read operation. The update flag, if 1, indicates CPU that 8257 is executing update cycle, and in update cycle 8257 load parameters in channel 3 to channel 2. Now I am going to discuss the remaining pins of DMA controller. What are the remaining pins? So here I have represented every pin with their correct pin numbers for 8257 DMA controller. This is a 40 pin IC and I've written all the pins here. So let's discuss the remaining pins. So there is a pin ADSTB. This is address strobe. TROB. This is the address strobe pin. This signal is used to demultiplex higher byte address and data using external latch. I am again repeating, this signal is used to demultiplex higher byte address and data using external latch. And then we have address enable, that is AEN. This is AEN. We have address enable. AEN. So what it does, this active high signal enables the 8-bit latch containing the upper 8 address system address bus. Again I am repeating what it does. This active high signal enables the 8-bit latch containing the upper 8 address bits onto the system address bus. Then the next I'm going to talk about is memory read and memory write, that is MEM R bar and MEM W bar. So these are active low signals. Why I'm saying, whenever I'm saying active low means this is MEMR with bar sign over it, so it will get activated when it is going to get 0 signal. So it is an active low signal. And then this MEM R bar signal is used to access data from the addressed memory location during a DMA read or memory to memory transfer, and MEM W bar signal is used to write data to the addressed memory location during DMA write or memory to memory transfer. Now the next, I've already discussed IO R bar and IO W bar signal. The next I'm going to discuss is CS bar. This is CS bar signal. This is an active low input used to select the 8257 as an input output device during the idle cycle. This allows CPU to communicate with 8257. Then the function of reset pin. This active high signal clears the command, status, request and temporary registers. It also clears the first and last flip-flop and sets the master register. Then the ready pin, this input is used to extend the memory read and write signals from the 8257 to interface slow memories or input-output devices. Then we have HRQ, that is hold request signal. As I've already told you what is the function of this HRQ is. Any valid DREQ causes 8257 to issue the HRQ. That is DREQ means DMA request. Any valid DMA request causes 8257 to issue the HRQ, that is hold request signal. It is used for requesting CPU to get the control of system bus. Then we have hold acknowledgement, that is HLDA signal. We have this HLDA signal. This active high hold acknowledge from the CPU indicates that it has this active high signal that is hold acknowledge from the CPU indicates that the CPU has released the control of the system bus. Then we have this DRQ0, DRQ1, DRQ2 and DRQ3. These signals, these are DMA request lines which are activated to obtain DMA service until the corresponding DACK signal goes active, that is your DMA request acknowledgement signal. So these are used to indicate this DACK0, DACK1, DACK2 and DACK3. These are used to indicate the peripheral device. Here the peripheral devices are there. These are used to indicate the peripheral devices that the DMA request is granted. So this was all about the block diagram and pin configuration of 8257 controller. Then we have priority resolver. Here is a priority resolver also, the remaining last block. So what it does, it resolves the peripheral requests. It can be programmed to work in two modes, either in fixed mode or in rotating priority mode. So here I have written also, these are the operating modes of 8257. So these are the operating modes of 8257. The first one is rotating priority mode. So in rotating priority mode, what happens? These are the channels, the DMA channels present in the 8257 DMA controller. So in rotating priority mode, the priority of the four channels has a circular sequence as given here. That is first channel 0, then channel 1, then channel 2, then channel 3, then again channel 0. So in this way it has a rotating priority, and the channel which is being serviced, it gets the lowest priority, and the channel next to it will get the highest priority for service. So thus, with rotating priority in a single chip DMA system, any device, any input output device which is requesting service is guaranteed to be recognized after no more than 3 higher priority services have occurred. Means if a device, if channel 0 is being serviced, or it is being serviced, it will get the lowest priority, and the channel 1 will get the highest priority. So every channel will get the chance, every channel will get a chance, and it will prevent any one of the channel from monopolizing the system. The rotating priority mode can be set by writing logic 1 in the bit 4 of the mode set register. As I've told you, this is the format for mode set register, and the bit 4 of the mode set register, if it is 1, then the 8257 will work in extended rotating priority mode, and if it is 0, then it will work in fixed priority mode. In fixed priority mode, the channels are having the priorities in this way. That is, channel 0 is having the highest priority, and channel 3 is having the lowest priority. And after recognition of any channel for service, the other channels are prevented from interfering with that service until it is completed. So what I'm trying to tell you, that if all the four channels are trying to get service or trying to transfer the data, so they will transfer the data as per the priority, as per whatever priority mode is set for 8257, depending on this B4 bit, whatever priority mode is set for 8257, depending on that priority mode, the channels will get prioritized and get serviced in the manner as mentioned here. Now the next one is extended write mode. The next operating mode is extended write mode. So the next is extended write mode. As we can see in the mode set register, we have auto load mode, TC stop mode, extended write mode, and rotating priority mode. So rotating priority and fixed priority mode I have already discussed. Next is extended write mode. We know that microcomputer system allows use of many types of memory and input output devices which are having different access times. So if a device, if any input output device cannot be accessed within a specific amount of time, it returns a not ready indication to the DMA controller. That causes DMA controller to insert the wait states, that is one or more wait states, in its internal sequencing. So this extended write option provides alternative timing for the input output and memory write signals, which allows the input output devices to return an early ready and prevents the unnecessary occurrence of wait states in the 8257 DMA controller. So it does this by activating MEMW bar and IOW bar signals earlier in the DMA cycle, giving more setup time. The next mode is TC stop mode. So if this bit of the mode set register is set, then a channel is disabled, that is its enable bit is reset after the terminal count output goes high, thus automatically preventing any further DMA operation on that channel. And to enable the DMA operation on that channel, it is necessary to set the enable bit of the corresponding channel in the mode set register. The next mode is auto load mode. In auto load mode, when it is enabled, it permits block chaining operations without immediate software intervention between blocks. In this mode, channel 2 parameters, that is DMA starting address, terminal count and DMA transfer mode, are initialized as usual for the first data block. These parameters are automatically duplicated in the channel 3 registers when channel 2 is initialized. So after the first block of DMA cycle is executed by channel 2, that is after the terminal count output goes high, the parameters stored in the channel 3 registers are transferred to channel 2 during an update cycle, and the next block of DMA cycle is executed. So this repeat block operations can be used in applications such as CRT refreshing, etc. So we have this three different DMA cycles: DMA read cycle, DMA write cycle and DMA verify cycle. So in DMA read cycle, data is transferred from memory to the input output device. In DMA write cycle, data is transferred from input output device to memory. In DMA verify cycle, in the cycle, data is not transferred between memory and input output device. It is used by the peripheral device to verify the data that has been recently transferred. To avoid overwriting registers of channel 3, update flag in the status register can be monitored by the CPU. So this was all about direct memory access controller. I'm ending this lecture here. Thank you.